Today we're covering some graphical methods for phase equilibrium. We covered in the previous class Raoult's law with dew point, bubble point, and flash, and now we're going to try to do this with graphical methods as well. So we used equations previously. We have Txy and Pxy diagrams that are going to give us vapor liquid. We're going to be able to perform the lever rule, and then we're also going to look at some solid liquid diagrams, and then three-phase liquid-liquid graphical plots as well. Okay, so just to jump right into a Txy diagram. Okay, so this is a Txy diagram, meaning that you have temperature versus mole fraction. Okay, so this is X or Y, and X would be the liquid mole fraction, and then Y is going to be the vapor mole fraction. Okay, so if we look at this, we see a couple different things. This is going to be a liquid region right here, and this is going to be a vapor region. So if you're at, for example, 70% N-pentane and 110 degrees Celsius, then that is going to be a vapor. Okay, and if you are cool it down to 60 degrees Celsius, then it's going to be 100, pure. It's just going to be pure liquid down here. Okay, so let me just explain a couple of the other features of this Txy diagram. We also have a dew point line and a bubble point line. So the dew point line is, as we come down in temperature, that's where the first drops of dew or liquid appear, and then as we continue down, you're going to be condensing more of it until this is the point at which, if you heat it up or cool it down, this is where the bubbles just first appear. Okay, so this is all liquid, and then bubbles first appear. This is all vapors, where it just starts to condense. So if we could just go to pure N-pentane, for example, and we have a vapor and we cool it down, we're going to condense here and then have all liquid. From this point, it's kind of like with water. We're very familiar with single component. Water, for example, if we heat it up, we'd reach a boiling point. It'll boil at one temperature and then continue as vapor. Okay, same thing with N. So this is going to be N heptane rich on that side, and that's going to be N pentane on this side. Okay, now if we also have 90 degrees, and then we just started adding more N-pentane, at a certain point we'd have our bubbles start forming, and then some of it would vaporize. As we keep adding more, it's going to turn to all vapor. Okay, and then we're going to be into the vapor region as we start adding more N-pentane. Okay, so let's also look at here's the different things for 2 atmospheres and then 1 atmosphere. You can see that everything is just shifted down for 1.5 atmospheres versus 2 atmospheres. Okay, so the reason why it shifts down is because you have a lower pressure, so more of it is going to be vapor. Okay, so let's look at this VLE phase diagram, and let's just go through some of these for this N-pentane and heptane. Now this is in Kelvin instead of degrees Celsius like before, and this is in atmospheres for the pressure. Okay, but again, the x-axis is going to be the x and y. Okay, this is going to be mole fraction of the liquid, mole fraction of the vapor. Now this is a Pxy diagram versus a Txy. So Pxy means that the pressure is going to increase or decrease, and Txy is the temperature is going to increase or decrease, but you're going to hold the other thing constant. So this is 1.5 atmospheres, and this is 400 Kelvin. So let's just answer this first one. What is the boiling point of N-heptane? Okay, so to get that, we could come over here and 0% N-pentane, and so that's going to be 100% N-heptane. If we come up to that, it's going to be about 386 Kelvin. Okay, so 386 Kelvin. Okay, what temperature would a liquid mixture of 40% N-heptane and 60% N-pentane begin to boil? Okay, so I'm going to come over here. This is N-pentane on the x-axis, and so if I start to heat it up, it's going to get to this point, and so that's going to be about 336 Kelvin. If I continue to heat it up, I'm going to have my last bit of liquid here, and then it's going to go to all vapor. So about 360 is the dew point for that mixture. Okay, so that's going to be all vapor. But what it's going to do is I'm going to have this in equilibrium, so it's going to start to vaporize, and then it's going to come back up, and then that's going to be my composition of my final vapor. Okay, and then at what temperature would a vapor mixture of 40% N-heptane and 60% N-heptane begin to condense? And that's this dew point that I just identified right there. So that's about 360 or 358 Kelvin. Okay, so let's go on here. Okay, and let's answer question number 4. What is the composition of the vapor in equilibrium with a liquid that is 30% N-heptane, 70% N-pentane? Okay, so this is the composition of the vapor. So here I have my liquid, and then in equilibrium with that, I draw it over here to the dew point line, and then come down, and that's going to be about 92% for my N-pentane in my vapor. And that makes sense because the N-pentane has a higher vapor pressure or lower boiling point. It's more volatile, and so you'd expect in the vapor for that to be in higher concentration. Okay, let's see. Now we're going to get on to what is the composition of the liquid in equilibrium with a vapor that's 75% N-pentane and 25% N-heptane. Okay, so let's look at this now. We have okay, so we have 75%. Okay, so I'm going to come right here. 75% N-pentane. What is the composition of the liquid in equilibrium with this vapor? Okay, so I'm going to come up to where the vapor is in equilibrium with the liquid, and then I'm going to draw this over to the liquid side, and then I'm going to come down to the liquid composition, and so that's about 38% N-pentane. Okay, actually that could have been right here, maybe about 40% N-pentane. Okay, so these are just graphical methods, mostly applicable for just two-component systems. So let's look at the PXY diagram and answer this 6th question right here. Using the PXY diagram, what is the vapor pressure of N-pentane at temperature for which the diagram was prepared? Okay, so 400 Kelvin, and then we want to check out what is the N-pentane vapor pressure. Okay, so I'm going to come over here to just pure N-pentane, and then come up to the pressure at which this goes from liquid to vapor. Okay, so at higher pressures, as the pressure increases, we're going to have liquid, and at lower pressures we're going to have vapor. Okay, so this is at 10.2 atmospheres. Okay, so we answered this. Let's go on to a last one. Okay. Okay, so let's just cover the lever rule. Okay, so on these diagrams we can also use these to determine how much liquid and how much vapor is going to be coming out of a feed with a particular composition and a particular number of moles of F, or our feed, and then we're going to be able to calculate the number of moles of vapor, the number of moles of liquid, and then the compositions of those as well. And so we can do this graphically. We previously did this with Raoult's law, calculated it from vapor pressures, they're temperature dependent. We can also do this graphically. And so here are the equations for deriving this, and I'll just show it to you graphically. So basically, if you have your feed here at this composition Z, and then you have your vapor and your liquid, we can get those because this is a particular temperature. The vapor and liquid are going to be in equilibrium with each other at a particular temperature, And if we're closer here to the liquid side, we're going to expect to have more liquid. Okay, as this dot, as the feed composition continues to go this way, let's say I'm right here, I'm just going to have pure liquid. If I come over here, I'm just going to have pure vapor. So if I'm closer to one side or the other, I'm going to have more of one or the other. Okay, so here I have distance A. Okay, this is going to be distance A, and then this total distance is distance B. Okay, and then what it's going to be is how much liquid I have is going to be A divided by B. Okay, and then I'm just going to label this C right here, this distance C, and then the amount of that's going to be the liquid. Okay, and then the vapor is going to be C divided by B. Okay, so that's just going to be the ratio of the distances. Okay, so if I get closer this way, then A is going to get larger, and I'm going to have more liquid. Okay, and then also C is going to get smaller, and I'm going to have less vapor. Okay, so that's how we do this tie line. So let's do this for this number 7 now. A feed stream of 30% N-pentane. Okay, is brought to this pressure of 1.5 atmospheres and a temperature of 360. Okay, so there's my temperature, and I started out with 30%. So I'm just going to climb this until I intersect with the temperature, and then I have my vapor and my liquid that's going to result from flashing this mixture. And if I just label this C and this A, and then the total one is going to be B, then the fraction, I'll just put the fraction of the liquid then is going to be A divided by B. And then the fraction of the vapor is going to be C divided by B. Okay, or B is equal to C plus A. Okay, so that's how we use the lever rule to determine how much of liquid and vapor are going to be there. Okay, so we had about 78% liquid in this case. Okay, so here are solid liquid phase diagrams. So we have, this. Oh, let me just label a couple things here. We have the eutectic point. Okay, it's kind of a funny name, but it's just going to be a phase. We call it. We have a couple different solid phases. We have solid B, we have solid A, and then we have eutectic. Okay, eutectic as well. So if we, for example, we have a liquid. Okay, at this composition, we start to cool it down. Then at this point, we're going to start forming solid B. Okay, so. And then as it continues down, we're going to have some solution of A and B. Now, this is more A as you go over to the right. So as you continue down, you're going to start making your solution higher concentration of A. But then you're also going to condense out solid B as well. And then at a certain temperature, it's just going to form solid B and then eutectic, which is also a solid. Okay, and we can also use the lever rule in this case. So let's just say this is distance 1, distance 2, and then my solid B is going to be distance 1 over distance 1 plus distance 2, and then my eutectic, okay, is going to be distance 2 over distance 1 plus distance 2. And that also works here as well. If this is distance 1 and this is distance 2, but my distance 2 over distance 1 plus distance 2, that's going to be for my solution of A and B. Okay, so this is a solid phase diagram. Just the different pieces of this, as I go through this. If we relate it to chocolate though, okay, so manufacturing chocolates, this is our phase diagram, a typical one, but this might be one for chocolate, for example. As I cool it down, I go from hot chocolate. I might get some solids precipitating out, but then this is going to be a chocolate phase. Okay, so I might have a eutectic point as well, and it's going to create different compositions here of in my solid phase for chocolate. There's a lot of science that goes behind chocolate. Okay, so what is a eutectic? Okay, solid crystals having a composition that is a mixture of pure components. Okay, in our prior example here, this was a mixture of 65% A and 35% B. So what I call my eutectic is really a mixture between A and B. So in this case, I had some solid B, that would be pure B. Okay, that would be in one phase, and then eutectic would be this combination of A and B. Okay, and it's not in equilibrium with any liquid solution, but maybe in equilibrium with a pure solid. Okay, so eutectic means that you don't have a eutectic with a liquid. It's always solid equilibrium. Okay, so here is my eutectic composition as we described, and let's just go on to a couple questions. Okay, so what phases are present for a mixture of 30% A? Okay, so I'm going to go 30% A at 320 Kelvin. Okay, so here I'm going to have solution and solid B. Okay, so what phases are present for a mixture of 60% A? Okay, at 320 degrees. Okay, in that case, I just have solution of A and B. Okay, and what phases are present for a mixture of 50% A? Okay, at 300 Kelvin. So there I'm going to have solid B plus eutectic. And then for a mixture of 80% A, what phases are present at 310? Okay, so right here, and there are my phases, solution plus solid A. Okay, so there I'm going to have my solution is going to be 68% A, and the rest is going to be B, and then I'm also going to have solid A at that point. And then how much of each phase is present? Then I can just use the, let me go back here and get the phases here. Okay. Looks like something just locked up on me. I'm going to go back there again. Okay, and okay. So for a mixture of 80% A, what phases are present at equilibrium of 310, and how much of each phase is present? Okay, so here is my solution plus solid A, and I can just use the lever rule. Okay, so this is going to be distance 2, let's say that's distance 1, and so solid A, I'm going to put just a fraction of solid A is going to be distance 2 over distance 1 plus distance 2. Okay, so let's just count the fractions there. Distance 2, let's say that is 0.13, and the total distance is 0.33, and the fraction of solution, okay, with this composition over here, 78%, is going to be distance 1 over distance 1 plus distance 2. Okay, and that's going to be 0.2 over 0.33. Okay, so let's just go on to a three-phase diagram as well. Okay, so I've got liquid-liquid equilibrium. I want to show you first of all a butanol water demo just to show the liquid-liquid equilibrium. Okay, so I have here it's going to be the water and the butanol. The water has some food coloring in it, so the water is going to be down here on the bottom, and then you have the butanol as well. Okay, and as you mix those together, they're going to form, they're going to mix them together, and then they're going to separate out into these phases. But we can also have a three-phase diagram. Okay, so let's just go over this one. What does the dark region represent? Okay, so let me just say a couple things about this three-phase region. There's A, okay, here's your composition of B, and then C as well. Okay, so those three, and then I can, this dark region right here is going to be a two-phase region. So this liquid is going to be in equilibrium. I have to follow this tie line here. Is going to be in equilibrium with liquid of that composition. So it's going to be two phases. Okay, and so let's just what phase? So the dark region is a two-phase region, and what phase is present at 10% A? Okay, so I'm going to come here to 10%. Along this line is going to be 10% A. And then 10% C as well. Okay, so this is 10% C, and then 80% B. So I'm going to be right at this point. So what phase, and then how much of each phase is present? So it's just going to be one phase. Okay, so it's not going to be two phase, and it's just going to be of that composition that we just mentioned. Okay, so what is the composition of the liquid in equilibrium with a liquid consisting of 82% A? So let's go down to 82% A, and then it's going to be 10% B. Okay, so 10% B. If I come right down here, okay, so there's my one liquid, and then I draw my tie line over, and I'm going to have another liquid that's going to be 25% B, and 70% A, and then it's going to be 5%, or sorry, 70% C, and then it's going to be 5% of A. Okay, and then what are the compositions of two phases in equilibrium if the total composition is 30% A, 20% B, and 50% C? So let's just go to A and go over to 30%. So let me erase some of these other lines so it doesn't get too mixed up here. Okay, so 30% A, 20% B. Okay, there's my 20% B, and then 50% C. Okay, so I only need to follow two of these over, and where they intersect, that's going to be my point. Okay, so there it is right there. And then I can use how much of each phase is present. So here's one liquid, there's the other. They're in equilibrium with each other. And so if I do my distance 1, distance 2, then I'm going to call this one, I'll say that's liquid 1, and then liquid 2. So my fraction of liquid 1 is going to be distance 2 divided by distance 1 plus distance 2. And my fraction of liquid 2 is just going to be 1 minus the fraction of liquid 1, or I could do distance 1 over distance 1 plus distance 2. Okay, so that would tell me the fraction of the two phases that are present for those two liquid mixtures. Okay, so that concludes this. What we're going to do for next time is also okay, so we covered some graphical methods for phase equilibrium. We looked at some TXY diagrams, some PXY diagrams. We took a look at the lever rule, and then we also had solid liquid phase diagrams. We took a look at the chocolate problem with these solid or solid liquid equilibrium, talked about eutectic points, and then went over these liquid equilibrium. So I just want to share one thing just at the end here, just this video of it mixing. Okay, so we have the butanol water. As we mix that together, it's going to be well mixed, and then it's going to come to two phases. Okay, so that concludes this lecture on liquid-liquid, solid-liquid, TXY and PXY diagrams.